Hello बच्चों, this is lecture number 14 of unit electrostatics, and in this lecture we will study two topics. First will be free charges and bound charges inside a conductor and electrostatics of conductors. First topic is free charges and bound charges inside a conductor. Free charges. The electrons in orbits near the nucleus are tightly bound by Coulomb attractive forces, while the electrons in outermost orbit are very loosely bound. In metals, these electrons are free and are not attached to individual atoms, but they can move freely throughout the volume of the metal and are often called the free electrons or free charges of the conductor or metal. In other words, we can say free charges are the loosely bound electrons of the outermost shell in an atom which are free to move throughout the conductor. Next is bound charges. The absence of electron from a neutral atom makes it positively charged, and the resulting atom is termed as positive ion. The positive ions are bound in the conductor in a regular pattern and are therefore termed as bound charges. Or we can say bound charges are the positively charged atoms called positive ions in which electrons are absent and they are fixed in a lattice. Second topic is electrostatics of conductors. In this topic, we will study some electrostatic properties of conducting body, and there are 7 points in that. First is electric field is zero inside a conductor. Second point is at the surface of a conductor, charged conductor, electrostatic field must be normal to the surface at every point. Third point is the interior of the conductor have no excess charge in a static situation. Fourth point is electrostatic potential is constant throughout the volume of the conductor and has the same value on its surface. Fifth point is electric field on the surface of the charged conductor is equal to sigma by epsilon naught n cap. Sixth point is surface charge is different at different point of charged conductor. And seventh and last point is electrostatic shielding. So let us understand these points one by one in detail. Electric field is zero inside a conductor, which is the first point. As we have studied in last chapter that E is equal to 0 inside the conductor and all excess charges reside on the outer surface of it. Here we will understand the concept behind this step by step. So, when a conductor is put into an external electric field E, let the direction of external electric field is from left to right, the free electrons of conductor experience a drift or force opposite to the direction of external electric field E. Then these electrons drive by external electric field on the left side of conductor, leaving the stationary nuclei or net positive charge on the right side, which are also called bound charge, as shown in figure. When electrons reach to the edge of the conductor, they pile up their negative charges on left and positive charges on right. Here we can see when conductor is put in an electric field, electron moves towards the opposite phase to the direction of the external electric field in the conductor, and they left the bound charges, that is positively charged atoms or positive ions, on the phase which is in the direction of the external electric field. Next step is these charges produce an electric field E internal of their own, opposite to the direction of external electric field E. As we can see, since there is polarization occur within a conductor, so there will be an induced electric field due to positive and negative charges from positive charge to the negative charge. Charges will flow until E internal will become equal to E external, and this process occur, that is motion of electrons from right face of the conductor to the left face and piling up there, occur until the internal induced electric field will become equal to the external electric field, and hence the net electric field in that situation will become 0, and now no charges will move inside the conductor. All the charges are static now on the surface of the conductor. The whole process is very instantaneous. In this way we can say that the net electric field inside a conductor is equal to 0, and all the excess charges reside on the outer surface of the conductor. Second point is, at the surface of a charged conductor, electrostatic field must be normal to the surface at every point. To understand this, let E is at theta angle on the surface, and hence force will also be at theta angle. There will be two components of force F sin theta normal to the surface and F cos theta tangent to the surface. F sin theta component leads the charges to accelerate normal to the surface, but charges cannot leave the surface because net force on the charge is 0 as they are static, and F cos theta component leads the charges to accelerate tangentially or move on the surface, which cannot be done because charges are static on the surface. Therefore, we can say F cos theta is equal to 0. Since F is not equal to 0, therefore cos theta must be equal to 0, and cos theta has the value 0 for theta is equal to 90 degree. And we get there will be no tangential component of force on the surface of the conductor, and hence E has also no tangential component. Hence E will be normal to the surface of the conductor always. Third point is, the interior of the conductor have no excess charge in static situation. To understand this, let us consider a small volume V inside the charged conductor, the net flux through whole surface S of this volume will be equal to 0 because electric field inside the conductor is 0. Then according to Gauss law, there will be no net charge enclosed by S, which is surface of the volume supposed V. If volume is considered as small as possible, or we can minimize this volume up to a point, so in that case we can say no net charge will be there at any point inside the conductor. Therefore, all the excess charges reside on the outer surface. So we can explain it by using Gauss law, and Gauss law says that the total flux through an arbitrary surface known as Gaussian surface is equal to 1 by epsilon naught times the net charge enclosed by that surface. And it says, according to the expression of Gauss law, if electric field is 0, then there will be no net charge enclosed by the Gaussian surface. Next point is electrostatic potential is constant throughout the volume of the conductor and has the same value on its surface. We will study it in two parts. First is inside the charged conductor and second is on the surface of the charged conductor. So inside the charged conductor, as we know that electrostatic field is equal to 0. Therefore, no work is to be done in moving a test charge between 2 points inside the charged conductor according to the formula W is equal to EdS. Therefore, no potential difference in there between any 2 points within it. At the surface of the charged conductor. At the surface, as we have seen in previous points, E is normal to the surface always and tangential component is 0. Therefore, work done will also be equal to 0. And hence, according to formula, potential difference delta V is equal to work done per unit charge. Potential difference will be equal to 0. And if the potential difference between 2 points is equal to 0, then we can say the electrostatic potential is constant throughout the volume at any point as well as on the surface of the charged conductor. Fifth point is electrostatic field on the surface of the charged conductor is equal to sigma by epsilon naught n cap. To prove that, let us consider a Gaussian surface partly inside and partly outside of the surface area ds on a conductor. Sigma is the surface charge density and the situation is shown in figure. According to Gauss theorem, E dot ds is equal to q by epsilon naught, and q can be written in the form of surface charge density as q is equal to sigma ds. By putting this value in above equation, we get E ds cos theta is equal to sigma ds upon epsilon naught. As the unit vector is normal to the surface in the upward direction. Thus, the angle between the electric field and area vector is 0. And we can write cos theta is equal to 1. So, by solving the equation, we get E is equal to sigma by epsilon naught along the direction of E. And by writing vector E as vector E is equal to sigma by epsilon naught n cap. N cap is showing the direction of electric field which is perpendicular to the surface. Second last point is surface charge is different at different points of charge conductor. When a conductor is placed in an electric field, the charges rearrange themselves. Therefore, surface charge density will be different at different points. It will be negative at the points having negative charge and positive at the points having positive charge. In this way, the surface charges are different at different points of the conductor. Seventh and last point is electrostatic shielding. Electrostatic shielding is the phenomena of protecting a certain region of space from external electric field. As we know that E is equal to 0 inside a conductor, therefore, to protect a sensitive instrument from external electric field, we put it into a hollow conductor. Such hollow conductors are called Faraday cages. Your homework is study the applications of electrostatic shielding and write it in your notes. Thank you.